Correspondingly, as Nicholas Copernicus introduced the heliocentric model, one more stunning rectification of how we could decipher the universe could emerge, beginning a conversation known as the rise of cosmology. This rise is marked by fundamental differences in our assessments and understanding of the universe's critical properties, like its age, size, and rate of development. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope JWST has intensified this conversation, presenting an image that challenges material science. So, what exactly is this crisis, and how does the JWST contribute to it? Well, contributing might be a bit misleading. It's more like a review that has been in progress. The crisis refers to a challenge to our understanding of the universe, particularly concerning its age and size, which are closely connected. The introduction of the JWST has been pivotal. Previously, we were limited in how far we could see into the early universe. However, with the JWST's advanced capabilities, astronomers can now explore much more distant galaxies, providing new perspectives and testing some of our past models. This advancement allows us to look further back in time, closer to the Big Bang, and observe galaxies in their formative stages. This provides crucial data that can either support or challenge our current cosmological models. To understand the crisis in detail, we need to explore the broader context. The standard model of cosmology, known as the hot inflationary Big Bang model or the lambda cold dark matter lambda-CDM model, has been particularly successful in explaining various components of the universe, from gravitational lensing to the structure of the cosmic web and the evolution of galaxies. This model suggests that the universe began with a Big Bang, followed by a period of rapid expansion, and has been expanding ever since. It includes components like dark matter, which exerts gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, groundbreaking observations, especially with advanced instruments like the JWST, raise the possibility that our current model may be incomplete or in need of revision. The lambda-CDM model makes specific predictions about the characteristics and behavior of galaxies at various stages of the universe's history. For example, it predicts that galaxies in the distant past should be smaller, less evolved, and contain fewer heavy elements compared to those in the nearby universe. This is because heavier elements form in the cores of stars and are dispersed through processes like supernova explosions, which take time to occur. This standard model also predicts the evolution within groups and clusters of galaxies and the properties of the cosmic microwave background, CMB. According to the model, galaxies should be smaller, bluer, less evolved, and poorer in heavy elements at greater distances. However, researchers have found evidence that challenges these expectations, resulting in a crisis in cosmology. The crisis centers on uncertainty about the age of the universe. Different measurement methods yield different results, leaving cosmologists struggling to reconcile these discrepancies. To resolve this, scientists use various techniques, such as studying cosmic background radiation, analyzing the expansion history of the universe, and applying mathematical models like the Friedmann equations based on Einstein's general relativity. The CMB is a critical tool for this calculation, providing essential data about the early universe's composition. Another method for determining the age of the universe involves observing Type 1 supernovae. These supernovae act as standard candles because they have a known intrinsic brightness. By comparing their known luminosity to their observed brightness, cosmologists can determine their distance and, consequently, the universe's expansion rate at different times. This approach played a crucial role in the 1990s discovery of dark energy, which is now fundamental to cosmological calculations. However, discrepancies remain. For example, the Hubble Space Telescope measured a faster expansion rate in the nearby universe, while the Planck telescope measured a slightly slower rate in the more distant universe. This discrepancy highlights the vastness of the universe and underscores the pioneering work of Edwin Hubble, who first proposed the universe's expansion rate in 1929. Modern telescopes have refined these measurements, but inconsistencies persist. These differences, though minor, around 10 to 20 million years in a universe roughly 13.77 billion years old, still demand careful examination. One possible explanation is that there may be flaws in our CMB measurements or gaps in our understanding of dark matter and dark energy. The JWST has exacerbated this crisis by revealing galaxies that appear to have formed much earlier than the standard cosmological model predicts. This discovery suggests our understanding needs a significant revision. The JWST's images show galaxies that are older and more developed than expected, raising fundamental questions about the universe's evolution and challenging the lambda CDM model. In conclusion, while the crisis in cosmology underscores the challenges and uncertainties in our understanding of the universe, it also highlights the importance of continued exploration and refinement of our models. The JWST's discoveries may ultimately lead to a deeper, more accurate understanding of the cosmos, much like Copernicus's heliocentric model revolutionized our perception of the solar system. The implications of this crisis are profound. If our current cosmological models are incomplete or flawed, it means we may need to fundamentally rethink our understanding of the universe's structure, origin, and ultimate fate. This potential paradigm shift would not only affect theoretical cosmology, but also impact our understanding of fundamental physics, including concepts related to dark matter, dark energy, and the laws governing the cosmos. Dark matter and dark energy. One of the most significant unknowns in cosmology is the nature of dark matter and dark energy. These mysterious components make up about 95% of the universe's total energy density, yet we still know very little about their true nature. Dark matter is believed to account for the gravitational forces that hold galaxies together, while dark energy is responsible for the accelerated expansion of the universe. However, if these components behave differently than our current models predict, or if entirely new forces or particles exist, this could explain some of the discrepancies observed with the JWST. Challenges to the standard model. The JWST's observations of galaxies that formed earlier and appear more developed than expected challenge one of the key assumptions of the lambda CDM model, that galaxy formation and evolution follow a relatively predictable timeline. The presence of large, mature galaxies in the early universe suggests that either galaxy formation occurred much faster than our models predict, or that there are unknown processes at play. This discrepancy could mean that the early universe was more dynamic and complex than we currently understand. The role of redshift. Redshift measurements, which help determine the distance and age of celestial objects, are another crucial tool in cosmology. According to the standard model, higher redshifts correspond to objects that are farther away and thus seen as they were earlier in the universe's history. However, if redshift measurements are being interpreted incorrectly, or if there are factors affecting redshift that we don't fully understand, this could also contribute to the crisis. The JWST's ability to observe high redshift galaxies with unprecedented detail has already led to surprising discoveries, and further research could reveal more about the true nature of these distant objects. Future directions and new models. To address the current crisis, cosmologists are exploring several potential avenues. 1. Refining observational techniques. Improved calibration of instruments and more precise measurements of cosmic phenomena could help resolve some of the discrepancies. Future missions, such as those involving next-generation space telescopes, may provide even more detailed data. 2. Revising theoretical models. If the current models can't explain the JWST's observations, new or modified theories may be necessary. These could involve changes to our understanding of dark matter and dark energy, or even entirely new physics beyond the standard model. 3. Multiverse hypotheses. Some cosmologists speculate that our universe might be just one of many in a multiverse, each with different physical laws and properties. While speculative, this idea could help explain some of the anomalies observed in the JWST data. 4. Reevaluating the Big Bang Theory. While the Big Bang Theory remains the best explanation for the origin of the universe, some of its assumptions may need to be reconsidered. For example, The initial conditions of the universe or the nature of cosmic inflation could be different than we currently believe. The broader impact. This crisis in cosmology is more than just a technical challenge. It represents a potential turning point in our quest to understand the universe. It reminds us that science is an ever-evolving process, where new discoveries can overturn established theories and lead to deeper insights. The JWST's contributions are a testament to the power of human curiosity and ingenuity, and they highlight the importance of continuing to push the boundaries of our knowledge. As Neil deGrasse Tyson and other leading scientists have pointed out, the answers to these questions may lead to a new era of cosmology, one where our current models are just the beginning of a much larger, more complex understanding of the universe. This is an exciting time for astronomy and physics, as each new discovery brings us closer to uncovering the true nature of the cosmos. In the end, the crisis in cosmology may not be a problem to be solved, but an opportunity to explore new frontiers in science. Just as Copernicus's heliocentric model transformed our view of the solar system, the JWST's findings could revolutionize our understanding of the universe, opening up new possibilities for exploration and discovery.